Okay, so before the break, we developed this inverse operator for a low-pass system, and we saw we can actually use it for solving differential equations. I have it written up here. This is basically the inverse operator for the 1 over the p plus a operator, where p is the Heaviside operator. It's just differentiation. And we derived that, and we used it to solve some basic problems. So we'll do 2 more problems. I'll just basically do a couple more examples that are circuit examples to see where that takes us. Okay? So let's do a circuit example. This time we will do one with inductors. So let's say you have a current source in parallel with a resistor and in parallel with an inductor. And let's say this is Is of t. This is your input. And let's say the current through the inductor is what we're looking at, I of t. So this is an inductor L and a resistor R. And this is a current source. So the question is, what is I in terms of Is, right? We have to write the expression again. We have to find what I is in terms of I of t. We have to first derive the differential equation, find the differential equation. How do we do that? Well, what do we know about the relationship between I and Is and this voltage? What is the relationship between the voltage and current of an inductor? We've derived this before, right? The voltage of an inductor, this voltage, is L di dt, because flux is L I, and the voltage is the derivative of flux with respect, magnetic flux with respect to the time. So that's V, and I know that this current plus that current should be this current. So I know that Is of t, or I can write it this way. I know that I of t plus the current through this resistor, which is what? What is the current through this resistor in terms of its voltage? It's the voltage across this guy and that guy are the same, right? So it's this V divided by the resistor, which is going to be what? So it's V divided by the resistor, but the voltage is basically L di dt. So if I want to write everything in terms of I's, I would get L over R di dt equals Is of t. Right? I just basically took this voltage, divided it by R to produce this current, and I said these 2 currents are equal to that, the sum of those 2 currents. So I can, again, multiply and divide by R. So this is, by the way, this is also a time constant. So if you have inductor circuits, the time constant for the capacitive circuit was RC, right? For inductor circuits, as you can see, is L over R, where R is the resistance seen by the inductor when all the independent sources are nulled. So this inductor sees a resistance across itself when you null all the independent sources. So if I null this one, this current source, what would it become? An open circuit, right? So what is the resistance seen by the inductor? R. So it's L over R. So in that sense, basically I have di dt equal, plus 1 over tau I is Is, or 1 over tau Is of t, which again is in the form of y prime plus ay equals x. Now, somebody over the break mentioned it, and it's correct. They said, why isn't it ax? And yes, that's correct. It should be really ax. But I'm thinking about this whole thing as a function. But that's why the scaling was messed up when we looked at it. But anyway, we'll keep it this way because it keeps it simple. So anyway, so this is what we have. You can actually even keep it, so this is in this form. You can also write it as I prime plus 1 over tau I equals Is over tau. Let's solve it this time, this way this time. Okay? Yes? Here, if I had a voltage source across here, the time constant would be infinity. Which means that if you have a voltage source here, this resistor doesn't exist. You're short-circuiting the resistor. So this is a short circuit here. There's no current flowing, there's no voltage. If you have a voltage source in parallel, you could have had a voltage source and everything would have been interesting, and you can do it as an exercise if it was like this. And that's not a problem, because then you get, what would be the time constant in this case? If this is R, this is L. L over R again, right? Because you null this becomes short, so the resistance seen across the inductor is R. But if you have it like this as a voltage source, then it basically short circuits it and nothing is left. So you have to be careful about those. Anyway, let's do it in this form this time. So let's see what I get. So this is, I can write this as P plus 1 over tau, right? I equals IS over tau. So I'm trying to find I of t. How do I do that? I of t is the inverse operator, which is 1 over P plus 1 over tau. Operating, and you can put the tau up here if you like, but it doesn't matter. Or 1 over tau, sorry. IS. So this 1 over tau is just a constant, right? So you can take it out. How do we calculate this? Who's next in line? Yes. So calculate the 1 over P plus 1 over tau of IS of t. Right. It's up here. I rewrote it. Yeah.
So you just swap that out to be e to the negative 1/2 t.
1/2 t? Oh, it's a tau. Yeah. Okay. So I haven't told you what e to the s is, right? So and I haven't told you what the tau is. So let's put some numbers on it. No, that's fine. That's fine. No, you were right. I mean, I didn't give you the information you needed. So let's say this is 4 ohms and this is 2 henries. So what is tau?
So it would be L over R, so
1/2.
So I just thought the tau looked like a 2.
That's okay. Or you were clairvoyant.
Huh?
Or you were clairvoyant. You knew that this is going to be the value, right? Okay, that's okay. Yeah. I know it looks like a 2. So now if that's 2, 1/2. So 1 over tau is 2 essentially, right? So this becomes 2 1 over P plus 2 and whatever the function is. So let's just give something. Let's just use something. We'll do different ones. So let's say the first thing we hit it with is e to the negative t u of t. So let's say is of t is that, e to the negative t u of t. So how do we do that? 2, 1 over P plus 2 e to the negative t u of t is what we're trying to calculate, right?
So then you have to replace it with what will be 2 times e to the negative 2t.
Okay.
Times 1 over p e to the 2t. And then whatever x of t was, e to the negative t.
Plus 2t e to the negative t u of t. So we have to integrate this thing.
Yeah, and then you just look like simplify it.
So you want to do it this way. That's fine. I mean, this time we were going to try to keep it just with this notation and see if we can handle it. So if this is e, basically essentially e to the t, right? The combination of these two. So we know that when we integrate those things, we can integrate it with that limits replaced by 0 to t, but then u of t comes out. So it's u of t integral of this thing from 0 to t, which is e to the t minus 1, which would produce what? 2, I'm sorry.
Yeah, so be 2 e to the negative t u of t minus, well, I guess you
No, when these two get multiplied, what do they get? Produce?
yeah, so you get e to the negative t u of t
Uh-huh.
minus e to the negative
2t u of t. So what happens? So this guy has only one real interest, right? One natural frequency, which is what? Which is e to the negative 2t kind of thing, right? This has one natural frequency. But I got two things at the output. What it naturally produced and what I excited it with, right? I said, yeah, look, this is really cool. Let's go and do, I don't know, hiking. Said, oh, let's think about, I don't know, this particular video game. Okay, all right, we can talk about both. So both came out. Yes?
How did you get from the 1 over tau over plus 1 over tau IST to 2 times whatever?
I calculated the tau for these values, right? The tau is L over R. So I said this is 2 ohms, 2 henries, 4 ohms. So this becomes 2 over 4, becomes 1/2 a second. And this is 1 over that, so it becomes 2. So this is 1/2, so the 1 over tau becomes 2. I just put numerical values on it. Just pick some values that are easy to deal with, essentially. Do you want to do another response to this, or we are good with this one? So you can see that it doesn't matter. I can put other things in there and apply the procedure and get that. Let's do something a little bit different to get us to something a little bit more interesting, at least at some level. Let's think about this. Let's just a voltage source Vs going to R, a resistor R, an inductor L, a capacitor C, and a resistor R. Now, you remember that when we talked about these capacitors and inductors, we said the capacitors and inductors really, you can express them in terms of the P operator as well, right? The currents and voltages, right? So for example, for a capacitor, we know I was C dV dt, which you can write as I is CPV. So, and we define this as the admittance of this capacitor, admittance operator. Or for an inductor, for example, we know V is L di dt, which you can write as LPI. And you can think about this as the impedance operator. And this was the admittance operator. So, but if you know these operators and we know that we can deal with them like rational functions, you can express the current and voltages of these things that way. So I can say, well, look, this is really LP and this is like CP, 1 over CP really, as a resistor. So it's as if these are resistors, the inductors and capacitors, but whose values are not just constants. His values are these operators. So I can treat them like resistors with these values. Because what's the resistance? Ohm's law, right? Ohm's law defines a resistor. So as long as I can think of this is Ohm's, this looks like Ohm's law. As long as I think of this as the resistor. So I can now treat these numbers as resistors, as values of resistors. And if I want to do that, if I say this is my output voltage, right, let's say, I want to find V in terms of Vs, or I want to find V for a given Vs, right? The step response of the system, the impulse response, or this response to some arbitrary input. How do I calculate that? Can I do that? Right? We can do it, right? I mean, just if these were 4 resistors, how would you do that? I mean, you can write the nodal equations, nodal analysis, and do the full blast nodal with these. But even if you were doing it in a more rudimentary fashion, in a high school fashion, or I don't know, middle school fashion, whatever, depending on where you learn it, elementary school fashion. So you can think about it as two different things. You can think about it as this resistor, which is the parallel combination of these two, and this resistor, right? And you have a voltage divider between two resistors, right? So this voltage in terms of that voltage is this resistor divided by the sum of two resistors. Do you agree? So I can write V of t as this resistor, which I can write as R in parallel with 1 over Cp divided by, and by in parallel, that's an operator, right? I mean, I can define this as AB over A plus B, the parallel combination. And then divided by R in parallel with 1 over Cp plus, now these two, which add because they're in series, R plus Lp. Okay? So what I need to do is I need to simplify this expression. This is like a little bit of a mess, but so I can write it in this form. I can write it as a product divided by the sum. I can write it as R, and then I get as 1 over R Cp. So these two multiplied and divided by the sum is that, right? If it's not clear to you, you can see it. Or if I multiply them, divided by the sum, and multiply both the numerator and denominator by Cp, this cancels, I get Cp here. Right, I get 1 plus RCp. So that is this. So I can write it as R over 1 plus RCp plus R plus Lp. Right? I'm treating them like rational functions, essentially. And I just basically add this and find a common denominator that cancels that common denominator. So I would end up with r there. I'm left with an r here. Or, yeah. Well, these two together give me r LCP squared. This guy gives me an r squared C times P. And this one gives me an L. And this one gives me an R, and this one gives me an R. I think that's the correct thing. Yeah, that's correct. So I can write it in, I can divide the numerator and denominator by, so I'm sorry, all of them are operating on Vs. So there should be a Vs in front of all of them. This operator operates on Vs to generate V. Right? So this is a new operator. I'm just finding what this operator is. So I can write it this way. So now V of t is that operator. I can simplify it by dividing the numerator and denominator by r. So I would end up with 1 over LCP squared plus RC plus L over R. You can see these forms. You will see them commonly, plus 2 Vs of t. Okay? So this is basically a new operator. Now, if I give you some numerical values for these components, so for example, the numerical values I've chosen is R being, both R's being 1/2 ohms, C 8 farads, and the L is 1 Henry. If you plug it in, you will see for those values, what you end up with is something like this. You will end up with 1 over 4p squared plus 3p plus 1 Vs. So it's just a bunch of values. Okay? So I mean, it can be parametric or it can be numerical, like this. I mean, semi-parametric. So, okay, so what do we do with this? Can we do something about that? Can you factor that? No? You sure? What is this? Two p plus 1. Let's see, I'm not even sure if I can factor that. Let's see. 4. 4, and then this should be 2, right? No, this is 1. You cannot, right?
Yeah, it's 4 times 1.
Right. You can factor it. No. You can always factor it.
Well, you can't get nice factors.
No, not even that. You can always factor it. It may become complex. And we'll get to that soon. So the question is that, can you factor it in nice forms or not? So it didn't. So whatever. So let's say whatever it is going to be some, you can write it in some form of factor, p plus a and p plus b. Right? If you do that, then for any arbitrary Vs, you can calculate it. The point of this exercise really is that you can actually, if using this operator, you can reduce these inductors and capacitors to things that behave like resistors and apply all those tricks that you know for resistors to capacitors and inductors with the operator. And that's the power of this operator. We'll do more examples of this going forward. But now this, if you really want to think about it, this is the transfer operator, what we call a transfer operator, because it takes the input and produces the output off of that. Right? So that's basically what we are going to be doing with a lot of stuff going forward. Now, in the most general sense, so let's talk this, just use this to kind of introduce something. We'll talk about it in more detail next time. If you have an nth order differential equation, right? Let's say you have bn y, nth derivative of y, plus bn minus 1, yn to the minus 1, all the way to b1 y prime plus b0 y equals Now, am x to the m, the mth derivative of x, again, am minus 1, x to the m minus 1, and all the way to a1 x prime plus a0 x. What do we do with something like this? You can think about it again. You can write this in terms of the operators, right? So you can write it as bn p to the n plus bn minus 1 p to the n minus 1 all the way up to b1 p plus b0. This giant operator operating on y is producing what this other giant operator operating on x produces. And what you need to do, you need to apply the inverse operator of this. So in general, you can write it like this gigantic thing in the denominator. You can write it as bnpn. And in the numerator, you have ampm plus a1 p plus a0 operating on x of t, producing y of t. But the good news is that we can deal with these things. How can we deal with something like that? How can we deal with the denominator? Well, we can at least factor it, and we'll talk about that. And then once we factor it, then we can go to what you suggested earlier, partial fraction expansion and all those things. But this whole giant operator that takes the input and produces the output, this is called the system operator. We show it with h of p. And this is an important operator. So this thing, we show it as, so it's an operator that takes this time domain function, it produces another time domain function. And we'll see how to find what this operator is, how to calculate it. But you can already kind of probably guess. If you can factor it, then you can break it into these small pieces that look like the one that we just did. And then once you can do that, you can break any nth order differential equation essentially down. And that's basically what we will be doing going forward. Any questions? No? All right, well, see you next time.